Welcome to Brunda Engineering Academy. In this video, we will do a quick review on thermodynamics. That means just the shortcuts. What are the shortcuts in the thermodynamics? It can be helpful for ECET, GATE, RRB exam and APPSC exam. In this video, we only discussed about in a short way of thermodynamics. Okay, it can be helpful for the examination point of view. It is just a quick review. First of all, in thermodynamics, the intensive property, intensive, intensive properties, intensive properties. Intensive properties means these are independent of mass. The properties which are independent of mass that are called as the intensive properties. Independent of mass are called as the intensive properties. Examples are the pressure, temperature, density, pressure, temperature, density, specific volume, specific heats, that means Cp, Cv, specific enthalpy, specific enthalpy. So these are the examples for the intensive properties. In the examination point of view, we ask like this: examples: pressure, temperature, density, specific volume, specific heat, specific heat constants, enthalpies. These are the intensive properties. These intensive properties means independent of mass, whereas extensive properties means these are depends on the mass of the system, okay. So examples are volume clearly. Next, energy, heat capacity, enthalpy. Here it is the enthalpy, it is the specific enthalpy. Observe the difference. So these are the extensive properties. Extensive properties means depends upon the mass of the system. That is the extensive property. Next, coming to that, the basic is about the pressure. Pressure here, pressure in terms of we have two terms, that is absolute pressure. Absolute pressure equal to atmospheric pressure, plus gauge pressure, If in our problem the gauge pressure is given, then find out absolute pressure by adding the atmospheric pressure and gauge pressure. Next, another way to find out the absolute pressure is P atmospheric pressure minus vacuum pressure. Atmospheric pressure minus vacuum pressure. Next, STP. STP means standard temperature and pressure. Standard temperature and pressure. STP means standard temperature and pressure. What is the standard temperature? That is T equal to, temperature is 15 degrees centigrade. Temperature is clearly 15 degrees centigrade. That means in terms of the kelvins, 288 kelvins. Whereas pressure equal to 1.01325 bar. 1.01325 bar. So that is also important in the RRB examination point of view. NTP means normal temperature and pressure. Normal temperature and pressure. Normal temperature and pressure. So normal temperature and pressure means the temperature is 0 degree centigrade. That means 273 Kelvin, 273 kelvins, and the pressure is similar to 1.01325 bar, 1.01325 bar. So these are the important STP and NTP. Next, coming to in our problems, we may thermodynamics heat supplied. Heat means represented by Q. Heat supplied. Heat supplied means we take it as the positive sign. Okay, please remember that. Heat rejected heat rejected. Heat rejected means you take it as the negative, minus sign you should take. Next, work done by the system, work done by system. Then you take positive sign. Okay, next work done on the system, work done on the system. You take it as the negative sign. You take it as the negative sign. Next, how can you calculate this heat supplied and work done? So, for that purpose, we have two types of systems. The work done in the closed system, work done in the closed system is given by integral of pdv. It is the basic relation. Work done for the closed system is integral of pdv, whereas work done in the open system is taken as integral of minus, here take it as outside, so that is minus vdp, minus VDP. It is for the open system, and closed for the closed system integral of PdV. For the open system integral of V minus integral of VDP. Next, after that, finding the Q. For the Q, dq equal to mcv dt. mcv dt is nothing, mcv, not cp, mcv t2 minus t1, mcv t2 minus t1. Next, coming to here, dH, that means enthalpy. Enthalpy can be calculated by mcp T2 minus T1. mcp T2 minus T1. And here, that enthalpy may be calculated by U plus P into specific volume. U is the internal energy, P is the pressure, and V is the specific volume. So, it is also the relation for the enthalpy, H equal to U plus PV. mcp T2 minus T1, here heat supplied is mcv T2 minus T1. And internal energy that can be calculated by mcv T2 minus mcv T2 minus T1, mcv T2 minus T1. So if you observe this, this can be written as Cv equal to dq by dt, dq by dt at constant volume. If constant volume, Cv equal to dq by dt at constant volume. Okay. Otherwise, it can be written as du by dt. du by dt. It is also correct. Whereas from this expression, we can write Cp equal to dH by dt. dH by dt. It is at the constant pressure. It is at the constant pressure. So next, one more important relation is the relation between the ratio between specific heats Cp and Cv is called as the adiabatic index, that can be taken as gamma. Cp by Cv equal to Cp by Cv equal to gamma. Observe the relation. Cp by Cv equal to gamma, and Cp minus Cv equal to Cp minus Cv equal to R. Cp minus Cv equal to R. That is also an important relation. Next, coming to some more points, that is basics of first law of thermodynamics, that is dq equal to du plus dw. It is the basic relation. Dq means heat supplied or rejected, that is change in internal energy, change in work done. Dq equal to du plus dw. It is the first law of thermodynamics. First law of thermodynamics. First law of thermodynamics is dq equal to du plus dw. Next, steady flow energy equation. Steady flow energy equation. Steady flow energy equation to the open system. To the open system. Generally, the steady flow energy equation is Q equal to, not Q, here Q plus m into V1 square by 2, V1 square by 2 plus H1 plus GZ1 equal to W plus mass into mass flow rate into here V2 square by 2, V2 square by 2 plus H2 plus GZ2. It is the steady flow energy equation to the open system, So here Q is the heat and M is the mass flow rate. V1 square by 2 is the energy, kinetic energy, or V1 is the velocities here. H1 is enthalpy and here GZ1, it is the potential energy, kinetic energy, potential energy, here enthalpy terms. Okay, so in the examination point of view, they will be asked about the applicable to the different applications, that is for the nozzle. Suppose the example is here nozzle. For the nozzle, the velocity equal to square root of 2 into h1 minus h2, velocity at the exit of the nozzle. Suppose here it is the nozzle, the flow will be in this direction. It is the first section and it is the second section. The exit velocity is V2 equal to square root of 2 into H1 minus H2. Or here V2 can be also written as V2 equal to square root of 2 Cp into T1 minus T2. T1 minus T2. It is also the important formula to find out the exit velocity. Exit velocity. In the nozzle, there is no, that is Q equal to 0. There is no work done. Work equal to 0. And the remaining terms GZ1. GZ is also equal to 0 in the steady flow energy equation. Next, coming to the next device, that is turbine. Turbine is the work producing device. In this turbine, only work will be there. We have to find out the work value. That work can be calculated by using the relation M into H1 minus H2. Work done is M into H1 minus H2. In the turbine, just these expressions can be derived from the steady flow energy equation. Here the turbine is, in the turbine, the terms here velocities are very negligible. And energies, that means potential energy is the 0 and there is no heat transfer in the turbines. Simply work done equal to M into H1 minus H2. Next, coming to the boiler. Boiler means it is the heat generating device. So here in the boiler, work done equal to 0. The expression for the boiler is M into H2 minus H1. M into H2 minus H1. Substitute work done is 0 in the steady flow energy expression. GZ equal to 0. GZ equal to 0. So then, and velocities, there is no movement in the body. There is no movement of fluid in the boiler, and velocity is also 0. If you substitute these values in the above steady flow energy equation, you get Q equal to M into H2 minus H1. Next, coming to condenser. Or first discuss about the compressor. Compressor means it is a pressure developing device. That means here we required work done, and some case of heat is also developed. So we get Q minus W equal to H minus H1 minus H2. Q minus W equal to H1 minus H2. So in the compressor cases, the velocities will be the 0 and the potential energy will be equal to 0. Next, coming to the condenser cases. Condenser. For the condenser, Q equal to M into H1 minus H2. Okay, so for the condenser cases, the same thing. Velocities are 0, GZ is 0, and work done is also 0. Here, in the compressor also work done is 0. Here, it is the compressor. For the compressor cases, Q minus W equal to H1 minus H2, and for the condenser cases, Q equal to M into H1 minus H2, M into H1 minus H2. So these are the different formulas related to the steady flow energy expression. Next, coming to here, heat engines, we have three different devices are there. One is the heat engine, don't get confused, heat pump, and a refrigerator. You have to calculate the we have to calculate the performance of these three devices. For the heat engine, efficiency is given by Q1 minus Q2 by Q1 minus Q2 by Q1. That means T1 minus T2 by T1. T1 minus T2 by T1. Whereas for the heat pump point of view, you have to perform COP, that means coefficient of performance. Coefficient of performance is Q1 by Q1 minus Q2, the reverse of the heat engine. That means T1 by T1 minus T2, T1 by T1 minus T2. Whereas coming to the refrigerator also, the performance is calculated by COP, that is coefficient of performance. Here cooling effect by work done, that is Q1 minus Q1 minus Q2, that is T2 by T1 minus T2. So by using these relations, they may be asked the problems. And another important relation between these three cases, COP of the heat pump, COP of the heat pump equal to COP of the heat pump, COP of the heat pump, the product of the COP of the heat pump and efficiency of the heat engine is equal to 1. COP of the heat pump and product COP of heat pump into COP of heat engine equal to 1. It is an important relation. Next, another important for the competitive examination point of view, uh, class inequalities. Class inequalities. Inequalities. The class inequalities are here three different processes are there. Here two different processes are there. One is the reversible process. Reversible process. For the reversible process, in entropy, that is dq by dt, s equal to dq by dt. Generally ds, that is change in entropy, equal to dq by dt, dq by t, that is nothing but entropy. It is the entropy. This integral of entropy equal to 0 for the reversible process, whereas irreversible process, for the irreversible process, this integral of dq by dt, integral of dq by t is less than 0. It is a confusion bit. For reversible process, dq by integral of dq by t equal to 0. For irreversible process, integral of dq by t is less than 0. If that is less than 0, that is irreversible process. If it is equal to 0, that is a reversible process. So that means for any type of process, this here dq by t is less than or equal to 0. It is the satisfaction. Integral of dq by t, it is any for any process, integral of dq by t is less than or equal to 0. And whereas if here, if integral of dq by t is greater than 0, it will be violates the second law, violates the second law of thermodynamics. So here it is violates of second law of thermodynamics. That means it is not possible. So integral of dq by t is greater than 0 is not possible. Always the process should be integral of dq by t is less than or equal to 0. So these are the important relations, basic fundamental relations in the thermodynamics in the competitive examination point of view. By using these formulas or these expressions, they may be asked about the different questions. In the next video, we will discuss about the remaining parameters, remaining formulas asked in the competitive examination point of view. So if you, this video can be helpful for a very quick review for examination preparation. If you have any doubts, please mention the doubts in our comment box, and definitely I will respond. If you like this video, please share and subscribe our Brunda Engineering Academy channel. Thank you.